My name is Scott, and I'm going to be talking to you a little bit about our Q sources today. So this is a brief agenda. What I'll be talking about today. Give sort of a brief overview of the Q sources portfolio. As we'll see, there are both acoustic exciters and structural exciters, so we'll spend a little bit of time on each of those. And we're going to start by really talking about what this quantity Q is. That may be new to you. If it is, hopefully you'll walk away today with a little bit better understanding. So first question, what is a Q source? Well, the Q sources that we offer, they're excitation devices. And as we talked about just a second ago, there's acoustic exciters and there are structural exciters. And depending on which your application is, one or both will fill some of your needs. And ultimately, our end goal throughout the whole conversation today is going to be directed toward measuring transfer functions, either direct or reciprocal transfer functions where we're putting some force or input into a system, be it a structure or an acoustic volume, and we're measuring some response. And the relationship between that input and output is called a transfer function, and that's what we're using these Q sources to measure. This could be used for system dynamics, so in a structural vibration application like modal analysis, but in a much more complex setup like a transfer path analysis, as well as in acoustics, you have sound quality, tire noise, things like that. In order to measure transfer functions accurately, you really should have some dedicated hardware. Most importantly is we want to be measuring the amount of input we're putting into the system. So if you're familiar with impact testing, you could be using an impact hammer to strike your structure, and it's got a load cell in that hammer, and it's measuring how many newtons you're putting into your structure. Same thing applies with Q sources. For the structural shakers, we're measuring newtons, just like with an impact hammer. And for acoustic sources, we're measuring this quantity called Q. And this is also known as volume acceleration. Okay, so when we talk about Q, it's really an acoustic force. And when we're talking about shakers, we're talking about a direct force in newtons. As well as being able to measure your input, you'd like to have constant sensitivity over the entire frequency range of interest, right? You don't want it to be really good at putting energy in at one area of your frequency range of interest and not another. And so we're going to be keeping good track of how well our exciters put energy into the system as a function of frequency. And then to that same end, you want to make sure that it has enough energy or power to excite your structure adequately across that frequency range. And so we're going to be talking about that as well. And then ideally for structural excitation, you'd like there to be negligible coupling between the system that you're trying to measure or characterize and then that input device. So with an impact hammer, you strike it and you're trying not to hit it a second time. You're removing the hammer's mass from the structure. After you hit it, you're trying to decouple the source from the system. So we'll be talking about how Q sources addresses that problem as well. So this is just a brief overview of the two sides of this family, acoustic and structural. You see we have 3 different acoustic sources and 4 different structural shakers we'll be talking about. And we'll cover each one of these briefly in the coming slides here, so I won't spend too much time. But just so you know, there's a total of 7 Q sources in our portfolio. So acoustic exciters, what is this quantity called Q? We talked about it being an acoustic force, but we're going to back up a little bit. So if we're measuring a transfer function, you see I've got input and output, and with a structural system, which I certainly became familiar with early on in my career, and this is the first transfer function that I measured, you're certainly putting input into the structure, and that's usually a measured force. Your output is typically measured with an accelerometer, and so your output is an acceleration. This is where we get our A over F, or acceleration over force. We create a bunch of these when we're doing a modal analysis, acceleration over force, transfer function. In the acoustic side of the world, we can do exactly the same thing. Instead of measuring acceleration, we're going to measure the acoustic output of our system. That would be a pressure, right? We're going to use a microphone. And for our input, we're going to use this thing called Q, or acoustic force, okay? So just like we have an A over F, we can also measure a P over Q. So what is Q? Well, if I have this sound source, and in this case it's a speaker, and I want to understand the acoustic force coming out of this speaker. It's a noise source. I'm going to be trying to quantify or measure Q. Well, we said Q was a volume acceleration. Well, how do I measure volume acceleration? Well, let's break this down a little bit. Think of this as really an area multiplied by an acceleration. So if we take this speaker and we break it down into some sub areas, if you will, and then I measure the acceleration, I measure an acceleration at these dots. So I could put an accelerometer in the center of that speaker cone. And if I was interested in the Q of the speaker cabinet here, I could also measure the acceleration up here. And I have a given area that I can measure that acceleration over. So I have an area and an acceleration, meters per squared times meter per second squared. That gives me meters cubed per second squared, or a volume acceleration. So this is how we measure Q in practice. So if I have a surface that is generating noise, and I want to understand where on that surface most of the noise is coming from, or I want to break it down into its different components, I can break that surface down into these smaller areas and then measure an accelerometer or measure an acceleration with an accelerometer at the center of each of those patches. So in this picture, I'm looking at an automotive instrument panel that's broken down into different areas. I could then put an accelerometer in the middle of each of those areas and come up with a Q, an operating Q for this vehicle under some load condition. And I would understand which areas produce the most sound or the most acoustic force. So I divide my area into smaller patches, measure an accelerometer or measure an acceleration in there. And as my frequency range of interest goes up, those patches need to get smaller and smaller. And that's really just due to the wavelength of sound and the physical property of sound at lower frequencies that gets bigger and bigger. And so at higher frequencies, that wavelength gets shorter and shorter. And so we need to use a smaller and smaller area to extend that frequency range. So this is how we measure a Q, kind of an operating or output Q. However, if we have a Q source, like we're talking about today, we can measure some really kind of interesting things. So again, our inputs are forces and acoustic forces, or Q, and our responses are acceleration and sound pressure, or A's and P's. So using these four letters for our two inputs and two outputs, we can come up with four different types of transfer functions. A over F, we've talked about that. That's an acceleration per unit force. Real typical impact hammer measurement or a shaker. You could also have an A over Q, where I'm measuring the acceleration on a structure due to an acoustic force. If you imagine that interaction between a loud sound or a sound source actually sending those sound waves out, causing the structure to shake a little bit, we could then measure that airborne, structure-borne interaction with an A over Q. Also have a P over F, which is a pressure per unit force. Again, this is very common in like a transfer path analysis where I'm trying to, let's say I'm working on an automobile and I want to understand what are the different paths or ways that energy is getting to the driver's ear. So my P is my driver's ear location with a microphone, and then I could essentially bonk on my structure at all these different places and generate a P over F. Similarly, there's also this P over Q where I'm measuring an acoustic response from an acoustic force. So I just want to know the transfer function, fully airborne. A over F, structure-borne transfer function. A over Q, airborne, structure-borne. P over F, airborne, structure-borne. P over Q, simply just airborne. We're going to see that there's a sort of a special relationship between this P over F and the A over Q. We'll take a look at that next. So very common measurement for a transfer path analysis in an automobile we were just talking about. We have this receiver location, this driver's ear, and we want to understand from our engine, let's say our engine or our motor in the case of an electric vehicle, this is our source. We want to know how much engine noise gets to our driver's ear through the engine mounts. So I've got some P, that's my target or my receiver, if you will, is the driver's ear pressure microphone. And we're going to make some impact measurements at the two engine mount locations. So in this case, I've got a simplified vehicle. I've got 2 engine mounts. So I could remove the engine, remove the mounts, take my impact hammer and hit the structure on the first engine mount bracket with my impact hammer. I'm measuring the F, I'm measuring the P response, and I would measure this thing called the P over F. How much pressure is produced by putting in force at this location. As I have 2 mount locations, I'm going to have to do a second measurement. So now I'm putting in my force here, and I'm going to measure a different function of P over F, where the F is applied at location 2. So I've got 2 locations. I create 2 P over Fs. This will help me understand how energy gets in and flows through my structure and produces noise at the driver's ear, given that the force is acting on my structure at either one of these mount locations. Now, in reality, I don't usually just have 2 engine mount locations, and I usually don't just care about one direction. I've only talked about the vertical direction here. In reality, it's more likely that I'm going to be measuring 3 transfer functions at each mount location, because I've got a vertical, a lateral, and a fore aft X, Y, and Z component to that force acting on my structure. So even in this simplified case, I've got 2 locations, but 3 directions each. So now I'm measuring 6 FRFs or P over Fs in order to quantify the structure-borne, airborne interaction. So now I've taken my impact hammer and I'm hitting each location at least 3 times, plus I'm taking a bunch of averages at each of those locations in each of those directions. And so you can see how the measurement time grows very, very quickly. And so we'd be interested in a more efficient way to do this, okay? This is what is called a direct measurement. Putting in a force, I'm measuring a pressure, I'm getting a P over F in the direct way. We can also measure transfer functions reciprocally, which means instead of putting my force or my energy into the system here and measuring the output at the driver's ear, I would do this the opposite way, as I would put my force in here at the driver's ear and measure my response at my mount locations. Now you see my forces have an X, Y, and Z component. With an impact hammer, I can only hit in one direction at a time. However, if I'm going to do this reciprocally, do we have a transducer that can measure the response in all 3 directions on that structure at once? The answer is yes, and I'll get to that in just a second. But first, I'm going to show you what allows us to do this. And this is sort of a simplified approach, but it does hold true. So if we look at that P over F transfer function, we look at the units involved in P over F. So pressure is a Newton per meter squared, or a Pascal, right? Over a unit of force, which is Newton. We simplify that down, and we end up with 1 over meter squared as our essentially reduced unit for a P over F. If I look at this A over Q function, and I do the same thing, area, acceleration, meters per second squared on the numerator, and then on the bottom is Q, or meters cubed per second squared, volume acceleration. You simplify those down, and you end up with the same units, 1 over meter squared. And this allows us to draw equivalency between a P over F and an A over Q. So instead of measuring the direct method and measuring all 6, 9, 12, 81 of these P over Fs in the direct direction, I can do this reciprocally with an A over Q. So now I'm going to be using a Q source as my acoustic force. I'm going to be measuring my response with an accelerometer. There are triaxial accelerometers, and this is where the advantage is really going to pay off for me, is I can measure X, Y, Z with one measurement, putting an accelerometer at my engine mounts, and then up here where my response was, I'm going to put my acoustic force. Because I can use the equivalency between a P over F and an A over Q, I can do all of these measurements in one shot and measure all 6 transfer functions, A over Q's or P over F's equivalent, by doing one measurement, okay? And realistically, I'm still going to be taking averages here. When you're doing transfer function measurements, you're always going to want to take a bunch of averages so that no individual hit or excitation is taken by itself. You can always have outliers. But the real benefit is I'm getting 6 for every one measurement I do. And this is the real benefit when you have something that can generate a measurable Q, like a Q source. So this is why we are interested in these devices, is that we can play some of these games and get some really interesting measurements. So let's take a look at these Q sources. These are the 3 acoustic exciters we have. All of them measure Q. And essentially it's, again, this game we play between I have so much acoustic energy I can produce. Are you more interested in low frequency with a high level or high frequency with a slightly reduced level? We have to sort of spread this energy out, either in frequency or amplitude. So you see this big guy, this QLMF, he is focused on the low frequency end of the spectrum, but can put out the most output. Then you have his little brother here, this QMed, which is a little bit smaller, more compact design, and we'll see why you might want one of these designs or the other. And then you have the QMHF, or mid-high frequency Q source, for your high frequency testing. All of these will be hooked up the same way, but just to give you an idea of how this works with your test lab and your SCADAS. So essentially, if you have a SCADAS front end, you're used to acquiring data, microphones and accelerometers, using the input channels here, but every SCADAS will also come with 2 source outs. If you've ever run a modal shaker or hooked up a speaker to your source out, you know this functionality is there. If not, you have 2 source outs, and this is a signal generator. You can have 2 channels of independently controlled signals. So essentially, we're going to send a signal out of the SCADAS. It's going to send it right to this amplifier, where there are specialized amps made to be used with these Q sources, essentially plug and play. So we're going to send this output signal, be it burst random or broadband noise, whatever it is, swept sine, amplify that signal, and then we're going to send that amplified signal to our Q source. In this case, this is a QMed. We're going to send that signal. This guy's going to generate our Q, and then we're going to be able to measure that Q as an output of the transducer and measure our Q on one of our input channels. So just like we would with a force impact hammer, we measure that force, we measure the response. We can do exactly the same thing with a Q source. In this case, it's an acoustic force generated by this Q source acoustic speaker. And then we use test lab in the traditional way. So that's how we hook these things up. We look at some numbers associated with each of these. You see both the QMed and the low mid frequency really focus on that sub 1000 hertz range. The big difference here is the QMed is a point source at all frequencies. So it's built to have a very small geometry, so you can fit it in a smaller location, like the trunk or maybe in the footwell of an automobile or some smaller place. You can see that it's only 75 millimeters by 200 millimeters, so pretty small. It's only less than 2 kilograms. And we'll see how it generates the low frequency. It's very kind of unique design. The LMF, this guy in the middle here, is purposefully built for driver's ear measurements, reciprocal driver's ear measurements. So it generates the Q right at the driver's ear position. You can move this guy up and down. But this cabinet you see down here is actually made to diffract sound in the same way that the sort of human torso does. Okay, so when you're doing vibroacoustic FRFs, especially for the interior of an automobile or something like that, that you want that diffraction pattern to be accurate for when there's going to be a human being sitting there. And we'll take a little bit closer look at that. And then the mid-high frequency obviously gets you up in the higher frequency range, also very, very high level. But ultimately, it's always a point source, and that makes it very convenient with this tube design. You can put this at the tailpipe, you put it at the driver's ear, you can put it at a tire patch, you can put it anywhere around the engine or alternator or cooling fans, anywhere you want to generate an acoustic force. This guy can go basically anywhere and allow you to be very flexible with how you measure your transfer functions. So this is the low mid frequency, again, very high level of output. So even if you have transfer functions down to the lower end of the hearing range at 20 hertz, you can adequately drive your structure. I have personally used one of these to measure the transfer function on the frame of an automobile. And when someone told me I could use an acoustic speaker in the driver's seat with the windows closed, play a noise and measure an acceleration on the frame of a full-size truck and get a decent measurement, I thought they were crazy. I have since done that with this piece of equipment. It's very good at generating not only broadband, but very high amplitude at those very low frequencies. So you can actually measure a response acceleration on a vehicle or other massive structure using an acoustic source in the passenger compartment as your exciter. Very, very neat. So then if you imagine in your TPA setup, it's not unlikely to have 50 acceleration locations. You're measuring all 3 directions of all 50 locations all at once with a single measurement. So it's very, very fast, way, 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 way faster than trying to go around to each of those locations and hit with an impact hammer. Not to mention all the repeatability problems you have with an impact hammer. And then you have the QMed. So the QMed operates a little bit differently in that it has a much smaller area, so it's got a much smaller driver, and so it uses 2 opposing pistons, essentially operate out of phase, which allows it to generate very high excitation, again at low frequencies, but always as a point source. So the geometry never really gets in the way in terms of diffraction like it does with the QLMF. Very different kind of feature size, but also application spectrum where you can put it any number of places. It's not restricted to the occupant seat like the driver one is. Then the Q mid high frequency, obviously we talked about its usages here, but TPA, airborne source quantifications, acoustic modal analyses, all of these can be used for all of these features. This guy is very nice because you can put it exactly at the tire patch essentially, or the tailpipe, or induction, snorkel, things like that. Very, very easily located point source. So if I move over to the structural exciters now, we'll kind of take a look at the other half of this family. And again, these are replacing an impact hammer or even a traditional electrodynamic shaker that you might hook up, with a stinger onto an object. And so you see, again, there's a family to cover the frequency range. Here we're using inertial mass to input the force to the structure. So as the feature size gets smaller, we're able to put in higher frequencies, QSHS or HSH, high frequency shaker. You can see it's very small, about the size of a United States quarter, and gets out above 10 kilohertz, but only puts in a very small amount of force because it's got a very low mass compared to. So at the other end, the thumper shaker, again, very good for low frequency. This is where you're traditionally using a sledge impact hammer. You could use this thumper shaker. And then the integral and miniature shaker are in between. These guys will get hooked up in very similar fashion, signal out from the SCADIS into the amp. That signal, all of these Q sources do come with a sort of a current protection device. So this will keep you from overdriving the shaker and damaging it. So this is sort of like a little fuse breaker if you want to think of it that way. It does not actually have a mechanical fuse, but that sends that condition signal out to the Q source shaker. And then from here, we're measuring, in this case, we're measuring both force as well as driving point acceleration. So not only do we get our force, but we also get an acceleration right from our mounting location. Very, very helpful feature of the Q source shakers. This is the family. You see, again, low frequency. The thumper shaker can put out up to 25 newtons RMS over the frequency range of 5 hertz to 200 hertz. Makes it very, very useful for bigger structures, big frames, or fully assembled vehicles, things like that. Then you have the integral shaker. Again, a nice balance between frequency range as well as being able to move it very quickly. Integrated accelerometer inside of it for a driving point accelerometer measurement. Miniature shaker, this guy gets you up to 5 kilohertz, so for higher frequency range. Again, very, very useful. Gets your attachment point mobility with both force and acceleration. And then you have the high frequency shaker for your very high frequency input. This thumper shaker, all of these shakers will feature this, what we're describing as self-suspension and self-aligning. So we talked at the very beginning about wanting to be as much as possibly decoupled between your input device and your responding structure, right? Well, we're physically attaching these shakers to our structure, and so we'd like them to be decoupled as much as possible. This proprietary suspension inside all of the shakers, but inside this thumper here, keeps essentially all of this inertial mass that you see here in this dark gray. This is the inertial mass that's going to be used to actually put the force in. That is decoupled from this portion that you glue on to the structure. So you see we glue it on here, then there's like a rod that goes through the inside. That is the only mass that's connected to your structure, essentially above the rigid body modes of the suspension, which is about 20 hertz or so. Okay, there's an internal force sensor, so you measure your force directly and can put in your force into your structure in any direction. So you essentially glue this foot pad onto the structure, thread this into that foot pad, and then you can make measurements in any direction with high degree of repeatability. The integral shaker uses this little force cup down here, and this force cup has an accelerometer mounted inside it. And so not only are you measuring the force from the transducer in here, but you're also getting your driving point accelerometer. Makes it very quickly moved around the test object. And again, very, very low mass actually being mass loading added to the structure because all you're adding is a little aluminum armature. This is a brief video that shows this decoupling. I'll show you the principle. Obviously, this isn't the real shaker, but you're seeing how the mass and the person's hand are connected with sort of a rubber band in this case. So above a certain frequency, the person's hand and the mass are totally decoupled. At low frequency, when he first starts out here, you see as the person's hand moves, so does the mass. And so you could say they're very directly coupled. But it's a function of frequency, right? It's the natural frequency of the system. If you're above that, you're in the isolation mode and your structure and your mass are decoupled. And that's why we have this internal suspension system in all of these shakers, where not only does it keep the mass decoupled from the structure, but it also allows the stinger of the shaker to be properly aligned. And so you're not putting in a moment into your structure, regardless of how you hang this thing. You're always just putting in a linear force. You're never putting in a moment or any kind of twisting force into your structure. The miniature shaker, again, feature size. So again, you can, where it would be impossible to put an impact hammer inside a combustion cylinder. I think there's a picture coming up of a piston rod and that mounting, never going to get an impact hammer inside there. So not only does the feature size help you, but it's also, we talked a little bit about the repeatability of these shaker systems. When I've shown these to people who are very familiar with impact testing, they come to expect a certain amount of reproducibility or coherence at certain frequency ranges for their given structure. And these devices really allow you to set it up, put it on 500 averages, go to lunch, and you can come back, and with 500 averages, you can get an incredibly good coherence between your input and your response at frequencies you'd never expect that are impossible with an impact hammer, just because without the human being involved lining it up and hitting at slightly different places at slightly different angles that they don't mean to, all of that's introducing variability into your test. None of that is applicable with a shaker because you're setting it up once and it's highly controlled. Yeah, so really feature size here. And then the high frequency, this is the smallest. And here the coil is actually glued directly to the structure. And so you can move these around very, very quickly. You could have 10 different excitation locations across your structure, set all of those up and essentially move the inertial mass portion from setup to setup to setup, and very, very quickly get your entire structure characterized with this high frequency. Again, places where a mechanical structural exciter has not been applicable, this guy can fit places never before possible, as well as get you frequency range that is kind of unheard of. Again, with the easy setup with TestLab, you can get hundreds of averages and really increase the coherency of your data. If you're interested, I've put up the website for the community site. If you're not familiar with this, I'll show you a little bit about it. But if I go out to the internet here, I'm just at Google and I just search SimCenter Q sources. You'll see that come up right here, SimCenter Q sources on the PLM community. So the community is a place where we like to put knowledge-based articles. You can ask questions of the test experts at Siemens as well as other users around the world. How do I do this in TestLab? How can I measure this quantity? Well, here on the knowledge base, you see there'll be QSource specific articles. So you'll see all of the QSource installation videos for all of the acoustic sources here. So if you want to see how we set this up, there's a video out here. You can go watch this guy set up a real test, goes over how to set it up in the software, but you'll give you an idea of all the things you could possibly be wondering about in terms of the application of these acoustic sources. So there's certainly all the acoustic ones, and there's always related links. This will be overall a sort of summary article on any Q sources, talks a little bit about what Q is. You see a lot of the same diagrams I've shown you here, but reviews all of the technical information, shows you some more application pictures from our engineering services department, as well as gives you some more additional information about the Q sources. So certainly highly recommend the community for any question you have, or if you're interested in learning more about what Siemens sells, either in data acquisition or processing software, as well as specialized hardware like our Q sources.